Okay, come on back to page 8. We're now going to talk about temperature and pressure in regards to equilibrium. Okay, so go ahead and write this down. If we have an increase in temperature, it's going to shift to lower the temperature. This is kind of like if you're hot and you're sitting in your car, you're going to turn on your air conditioner, right? On the opposite of that, if we decrease the temperature in a reaction, it's going to shift to raise the temperature. So again, if we're cold and we're in our car, we're going to turn on our heat to help raise our temperature. Okay, so when we look at temperature, we have to now go back and talk about endo and exothermic reactions. So please remember that endothermic is when reactions have heat as a reactant. So on top of this in your paper, I would go ahead and I would just write down endo on top of this reaction to show that this is an endothermic reaction because of that heat. Another thing you can look at is a graph. Remember, on a graph, the products are going to have higher energy than the reactants. The other thing you can look at is that your delta H is going to be positive if it's endothermic. So for example, on here, if this is 40, and let's say this is 10, if I figure out my delta H, 40 minus 10 is equal to 30, and that is a positive delta H. So those are 3 different ways you can tell if a reaction is endothermic. Okay, now exothermic, remember, is when heat is a product. So on this one, I would write exo on the top of this box. And again, you can tell because heat's going to be on the product side. Another way to tell is by this graph, the products are going to be lower energy than the reactants. Another way to tell is the fact that your delta H is negative. So on this one, let's say that our products are 10, that our reactants are at like a 30. If I do 10, which is our products, minus 30, I'm going to get a negative 20, which of course is a negative delta H, so that means this is an exothermic reaction. Okay, so let's look at how we use these. So here's a reaction. On this one, notice that the word heat isn't there. So remember, heat is just a form of energy. So if you ever see the word energy, you can think, oh, that's going to relate to heat. So this is what I like to do. I'm looking at my delta H. Because my delta H is negative, this means this is an exothermic reaction. So I'm going to add the word heat to the product side. I like to do this because temperature is just like concentration. If we add temperature, it's going to go away. So if I add temperature right here, because it's on the product side, it's going to shift to the reactant side. If you remove heat or lower heat, it's gonna stay on the same side. So concentration and temperature, you can use this little saying to help you remember how things work. Okay, so first question. Predict a right or left shift if we increase temperature. So look at where the temperature is. This is your heat. If we increase it, it's going to go to the opposite side. So since it's on the reactants, the product side, it's on the right side, it's going to go to the left side. This is going to shift to the left side. Okay. Remember with temperature, okay, when I'm increasing the temperature, what I'm really doing is trying to shift it so that it lowers. Okay, we're always trying to make that balance, that equilibrium. So that's going to go to the left. Okay, the next one says we're going to decrease temperature. So again, here's your heat. If we decrease, that means the same thing as removing it. It's going to stay on this side. So now it's going to stay on the right side. So this is going to be right. It's going to shift to the right. Okay. And then B says, what effect of hydrogen if we increase the temperature? So we know that if we increase the temperature, it's going to shift to the left. This is all kind of messy. Let me erase some things. Okay. So right here, if we increase our temperature, it's going to shift to the opposite side. So now we're going to increase anything on that reactant side, decrease anything on that product side. So hydrogen is on the reactant side. Notice how it is in front of this arrow. So this means we're going to increase the amount of hydrogen produced. Okay. Now what's happening here with heat is that if we increase our heat, it increases how fast those molecules move. They move faster. When they move faster, there's more collisions, When there's more collisions, there's more probability that a proper orientation to create that product will occur, and so therefore you're going to create more products. So that's what's happening on the molecular level with this heat being added. Okay, let's do some examples now. So if you want to go ahead and do this on your own, pause the video, and then once you're done, come back and check your work. That would be awesome. Okay, this arrow should be double-sided to show equilibrium. Okay. Let's go ahead and talk about this one. Direction of shift if temperature is lowered. So on this one, we see that heat is in the reaction. Okay, it's right there. This shows us that it's endothermic. So if we lower that, remember, it stays on the same side. So it's going to stay on this left side. So this first question is left. It just means it's favoring that reverse reaction because more reactants are being produced. And then it says effect on carbon dioxide if temp is lowered. So look at where the carbon dioxide is. It's right here. Notice that the carbon dioxide is in front of this arrow. The arrow is pointing towards it, so that means it's going to be increased. Okay. All right. So here's what's happening here. If we decrease the heat, the molecules aren't going to move faster. So that's why it stays on that same side, because we're not going to make more product. Okay, let's go to the next question, the next slide. Okay, here's our whiteboards here. So on this one, let me try something. My little marker wasn't working. Okay, coming back to my marker, here we go. Okay, on this one, it tells us that we're dealing with heat, but we don't have heat in the reaction. So look at your delta H. This is positive. Remember, positive means endothermic. So I'm going to write in heat on this reactant side to help me remember that it's on that reactant side. Okay, so first of all, is heat a reactant or a product? It's going to be a reactant because the delta H is positive. If we increase our temperature, let me read that again. Increasing temperature will shift equilibrium which direction? So if we increase this little dude, okay, it's on the left. That means it's going to shift to the right. So it's going to shift to the right. It's going to produce more products. Okay. All right. Now I'm just showing you this because now you can do the questions that talk about heat on page 12. Okay, going back to page 8, let's finish and talk about pressure. Okay, with pressure, this deals, if we increase the pressure, it's going to shift towards the least number of moles in the gas state. Okay, the gas state is very important when we're talking about pressure. Okay, in a gas state compared to solid and liquid, a gas can condense when the temperature gets colder, and it can expand when the temperature gets warmer. So what I want you to think about is if you have an inner tube and it's a hot sunny day, and you're going to go float in a tube. If it's warm outside, your inner tube is going to feel very firm. If you filled it up, it's going to feel very firm. Let's say it starts to rain and the temperature goes down maybe by 10 or 15 degrees, which is pretty extreme, but anyway, go with it. If that goes down and it gets colder, those molecules aren't going to move as much. Therefore, we're not going to have as many collisions, and so your gas is going to condense, and now your tube is going to feel kind of flimsy. Because those gas molecules are condensed. So that's why we're only dealing with a gas state when we're dealing with equilibrium problems. Because solids and liquids, they don't have that issue as far as the compression. Okay, so here's a question. Predict a right or left shift when we increase and decrease the pressure. So let's start with increase, okay? The first thing we have to do whenever it talks about pressure is find out how many moles of gas we have. So these little things right here, this tells us that it's in a gas state. If it says S, that means it's a solid state. If it says L, it means liquid state. If it says AQ, this means aqueous, and aqueous just means that we have dissolved that substance in water. So if it says something like NaCl, that means that salt has been dissolved in water. Okay? So let's first figure out how many moles of gas we have. So right here, we have a gas, And moles are just represented by the coefficient. So on the reactant side, we have 2. On the product side, these are both in the gas state. We've got 1 here, 2 here for a total of 3. So I write that on top of my reaction so I remember how many moles of gas I have. So the first thing is increase the pressure. When we increase pressure, it's going to go to the side with the least number of moles. Just think about this as a teeter-totter, okay? We're always trying to make our teeter-totter balanced so that it's like an equilibrium. We don't want it to be one person up in the air or the other person up in the air. We want it to be balanced like this. So if we increase pressure, it's going to go side with the least number of moles. And that is going to be that left side. So this is going to shift to the left. Okay, if we decrease pressure, it's going to go to the side with the most number of moles. So that means it's going to go to the right side because the right side has 3 versus 2. So this would be right, that second answer. Okay, then it says effect of chlorine if the pressure lowers. Well, we know if the pressure lowers, that's just a decrease. So what we're looking at if it lowers, so we're looking at it shifting to the right. Where's chlorine in conjunction to that? Chlorine is right here. It's in front of the arrow. Okay, this chlorine is, which means that it's going to increase. So that chlorine is going to increase because that arrow is in front of the arrow. Okay, let's do some other problems now. Okay, so right here, we've got this equation. And the first thing it's saying is, are reactants or products favored in the following scenario? So the first one is heat is added. So heat is dealing with temperature. So once again, we have to look to see if we have heat in the equation. We don't, so we're going to use our delta H. Our delta H is negative. Negative means exothermic, so we're going to add heat right there. Okay, and if heat's added, remember heat, add away, remove it stays. So since heat's on that product side and we're adding to the heat, it's going to shift to the opposite direction of where the heat is, so it's going to shift to the left. Okay, that's what's happening there. Let's look at our next one. Our next one is, heat is removed. So again, we have to know where heat is. We already wrote this down. Sorry that it like erases, but we're going to put plus heat right here. So if heat is removed, removing something that stays on the same side, since heat's on the product side, it's going to go towards that side. So this is going to be on the right side when heat is removed. Okay. Next one, pressure is increased. Okay, whenever we see pressure, we have to look at the number of moles of gas. So right here, notice we've got gas, gas, gas. So let's add up how many moles we have. On this reactant side, we have 3 plus 1, so we have a total of 4. On this side, we have a total of 2. Okay, so now it says pressure is increased. If pressure is increased, it goes to the side with the least number of moles. So that means it's going to go towards the product. So that means right. Okay, last question. Pressure is decreased. So again, we have to look at our number of moles. Okay, so here we still have 4 moles on the reactant side, 2 moles on the product side. If it's decreased, it goes towards the side with the most number of gas moles, which is to the left. So this answer would be left. Okay, I hope this makes sense so far. Let me just show you one other thing. Let's say that instead of having gas here with nitrogen, let's say that this is a solid, okay? Or it could be a liquid, anything other than a gas. So if I'm adding up how many moles I have in this equation, I've only got 3 moles of gas on the reactant side, and I still only have 2 moles of gas on the product side. So if you see a solid or a liquid or aqueous, do not add that when you're adding the amount of moles you have in a gas state. All right, let's do, oh, I guess that was it. That was our last question. Okay, I hope this helps. Please let me know if you have any questions. Feel free to email me. And the test, we're planning on having a test on Friday. So if you feel ready for that, send out an email, and good luck.